So for this segment, what we'll be talking about is like how to find out the domain and range of three specific functions, which is one is the log function, second is your basic, what do you say, polynomial function, and third one is a rational function. So when you start with a polynomial function, just remember that when you have a polynomial function, I mean, it has to be of the form ax to the power n plus bx to the power n minus 1 and so on until a constant. It's like a quadratic function. Let's see, talk about any quadratic function like 2x squared plus 3x plus 5. Now, this, if you talk about the natural domain means for sometimes you get the restricted domain where you restrict only between certain x values. So I'm not talking about that. I'm just talking about the natural domain. Any polynomial function, including y equals to constant. Y equals to constant is like a line, is always defined for all real numbers. So any quadratic that you would have done, you always said the domain is all real numbers generally. So any polynomial function when you have, it is going to be defined for all real numbers. So just remember, a polynomial function, say that domain is all real numbers. Now coming to the second part, which is like rational function. A rational function is something that we need to talk about. Now, when you talk about rational function domain, let's say if my function is 3x plus 2 over x minus 5. Now, if I make the denominator 0, at that time, my function become undefined. So whenever you say uh, that you have to find out the domain for the rational function, you just do one thing is equate denominator to 0. So when I equate denominator to 0, I get the point where it is actually undefined. So when I say that, okay, x equals to 5, actually this is referred as a vertical asymptote, where the function cannot have a finite y value. So when x is 5, your function is undefined. Now at the rest of the points, your graph is defined. So when you say x belongs to real numbers and x should not be 5, as simple as that. So this is called as this will be the domain for this function. Now let's talk about the domain for some more complicated functions, which are in form of rational functions. Sometimes you'll get like a part of the graph like x squared plus 1 over x or something. Now out here also, you see that the function is actually undefined when denominator is 0 here. So you straight away say x belongs to real numbers, x should not be 0. Any x value that makes your denominator 0 will be excluded from the what you call it as the domain. Now, any specific functions, for example, let's say if you have f of x as 3x over x minus 5, x minus 2, x plus 7, where you have multiple functions for which denominator is undefined, those all the points will be excluded here. So x, you'll see simply say x belongs to real numbers, x should not be 5, x should not be 2, and x should not be negative 7. What is really interesting is a particular concept and type of question that actually is assessed again and again in DP course is basically where you see the concept of a whole. Now, lots of time we get like a question like find out the domain for x squared minus 4 over x minus 2. Now, lots of time the intuition says it's okay, x belongs to real numbers, but x should not be 2. Here, the ideal scenario if you would have followed. So what actually happen in some cases are that if you factor out the numerator, your denominator actually get cancelled. So it means that actually 0 was a factor of both the numerator and denominator. So if I ignore this, like if I cancel out this part, I get only x plus 2 function. So actually when you do the graph of this function is not any more like a complicated graph. It's just a straight line y equals to x plus 2. But how it is actually different from actual x plus 2 function? How it is different? Is it the same thing? Is it different? So how, if it is different, how it is different? Actually, what you did is here, this is actually a blunder that we did. When you can strike out 0 by 0, I mean, this is something that we are like canceling out that, okay, for x is x minus 2, x minus 2 are canceling out. Now, logically speaking, if I would have plugged x as 0 here, x as 2 here, and x as 2, it would have made my 0 by 0 format. Now, generally, when your numerator and denominator have a common factor and they are getting cancelled, at that point, the graph will not have actually the proper value. It will be a hole. So at x equals to 2, this is not going to be an ordinary x plus 2 line. This is going to have the definition at this point will be a hole. So here what you see at x equals to 2 will be actually in this point, there will be a hole. So at this point, your y will be undefined. And you can test it by plugging x as 0 here, if x as 2 here, because 4 minus 4 upon 2 minus 2, which is 0 over 0. And I can't say 0 over 0 is like some number. If I plug x as 2 here, you'll see it is 2 plus 2 is 4. It means according to this equation, it is coming as 4. So in such cases, you need to say that there is a hole that exists, and you need to find out when you can factorize the expressions, like when you can see that, let's say the factors are easily getting cancelled. Now, for example, if I had x minus 2 here, at x equals to 2 would have been whole. If I had x plus 7 here, x equals to minus 7 would have been also whole. So at that point, actually, the graph will be undefined. Now, if I have to show you the same thing on, like, let's say decimals or something, let's just check how it. So now when you see it's the same function that I have taken, x squared minus 4 over x minus 2. This is actually the same stuff here, but actually if you go at exact 2 point, when I go at 2, it looks like the function is continuous, but you can see that the hole is clearly visible at that point. So you can see that there is a dot, there is a void that you can see on the graph that my cursor is currently pointing to. So this is the concept of hole. If I had, let's say, taken even, let's say, x minus 2, and if I would have taken x plus 2 also, at that point, you will notice that there is a hole at 2 points, at negative 2 as well as positive 2. So when I go at negative 2, you'll see that it is undefined. And even at positive 2, this is undefined. So it's not a ordinary y equals to 1 line then. So that's where you need to understand the concept of hole becomes really important. And when there's a hole, you say that the graph is defined for all real numbers apart from those two, the whole points. So that's how you tackle the concept of hole. Now let's go back to our rational function domain and range. So now, more or less, we covered on this concept, how to find out the domain for the rational function. Now we have the last fragment, that is the domain for logarithmic functions. Now, even though you don't have idea about logarithmic functions, I'm just writing out a little bit about the log functions so that you can just catch up later on. If you have log is just an operator. It's like an ordinary function where you take the log of certain number and to the certain base. Now, here both numbers a and b must be positive. A and b must be positive. That's a requirement. At the same time, b should not be 1. That's the requirement. At this stage, if you don't understand log property, that's okay. But just remember this as a thumb rule for finding the domain for the logarithmic function. Now, for example, if I'm finding out the domain for log of x squared minus 4x plus 4, or let's say x squared minus 4x plus 3 to the base 2. Now, how do I do this particular question? So when I find the log domain for this question, my only requirement will be 4x squared minus 4x plus 3 should be higher than 0. Now, when you factor this out, you get x minus 1, x minus 3. You take 1 and 3 here, and once again, you sketch the sign diagram, negative, positive, positive, negative, positive, because it's a happy face graph, parabola. So here you can see that this graph is positive at this point and at this point. So where x is greater than 3 or x is less than 1. That's how you find out the domain for the logarithmic function. Now, in some cases, your base is also like, let's say, for example, if I've got log x squared minus 3, x squared minus 9, and to the base x plus 2. So now in this case, x plus 2 should not be basically, x plus 2 should not be negative 1. I mean, should not be 1. That's another added condition apart from x squared minus 9 being positive. So if I take x squared minus 9 strictly greater than 0, I get answer is negative 3 and positive 3 here, which becomes basically negative positive, and positive once again. So according to this, my domain is x greater than 3 or x less than -3. But if you blindly do that, number one, you go wrong is the second rule that b must be always greater than 0. So now in this case, if you see x is less than -3, that is strictly cutting the rule that if I take x is less than -3, like for example, I take -4, okay, this is coming positive, but these become undefined because base and main number should be both positive. And one added condition comes that the base should not be basically, what do you say, it should not be 1. So what you can say is that x here should not be -1. Anyways, when I look at the domain here, so this function you can say will be strictly defined for x greater than 3. And now let's check out how does it actually look like on a Desmos function. Like how does this actually is applicable to the Desmos graph. Now if you see the function here that I'm going to feed is, I'm just going to take the log function from miscellaneous ones. So log base is x plus 2. So I'm going to take base here is x plus 2. And this number is, main number is x squared minus 9. So you can see the graph is actually no more defined for any other values apart from x greater than 3. So you can see that there is no existence of negative values because they were cutting down the base. But if I had some normal base, in that case, you will notice that the graph is actually defined for both the sides then. So you can see that here is the new domain, x greater than 3 or x less than -3. Both the sides it become defined. So you need to consider both the numbers in order to make the final answer practical and correct. So that's how you find out the domain and range for the logarithmic functions, the basic functions that are polynomial functions and so rational functions. We'll do some more types of functions like exponential functions and other stuff when we're doing each of them more particularly. So for now, this is the basics of the domain and range.